So this beginning is about polyprotic acids. What is special about polyprotic acids? um, more than one what? Hydrogen that is acidic. More than one acidic hydrogen. FYI, vocabulary, another way to describe an acidic hydrogen is to say it's a labile hydrogen, meaning that it can easily be removed when it's in water. Okay? So, carbonic acid is a diprotic acid. Diprotic means that it's two acidic hydrogens. Polyprotic just means that there's more than one. Polyprotic is like the general. Di means two. Tri would be three, so on and so forth. Okay? So we are going to write out the two dissociation reactions that shows the diprotic behavior of carbonic acid. Before we do that, though, what type of acid, don't say diprotic, what type of acid is carbonic acid? It's a weak acid. How do you know it's weak? There's carbon in it. What if I didn't tell you the structure? What else in the problem tells us that this is a weak acid? But sulfuric acid has two dissociation equations, and that's a strong acid. So it's not all polyprotics are weak. Most of them are, but not all of them are. So what else in this problem? I heard somebody say it. The equilibrium constant. We have a Ka value. Remember, I'm not going to give you equilibrium constants for strong acids. We only care about the equilibrium constants for weak acids and bases. Okay? So since we have a Ka value, and that Ka value is fairly small, that means that carbonic acid is a weak acid. Got it? All right, so we've actually already written out the dissociation equations of carbonic acid on the first day, so let's review that. Remember, polyprotic substances, polyprotic acids, dissociate one hydrogen at a time. Okay. So our first equation will be the dissociation of carbonic acid into what two ions? HCO. What's the rest of it? 3 minus, and? Well, for this one, it would be H plus. It would be H3O plus if we added carbonic acid to water, which would be perfectly acceptable. Okay? I was just writing out the straight dissociation, not the Bronsted-Lowry reaction. We're going to review the Bronsted-Lowry reactions with letter B. Okay? So there's my first dissociation. So if we wrote the equilibrium expression for that first equation, we would call that Ka1. Okay? And then for the second dissociation, what is going to be my reactant? HCO3 minus, and then what would that dissociate into? Plus H plus. And if we wrote the dissociation equation for that, or sorry, the equilibrium expression for that, it'd be Ka2. Got it? All right. So now let's actually do some calculations with this. So if we assume that only the first dissociation occurs, we're going to calculate the H plus concentration of a 0.1 molar carbonic acid solution. Now remember, when we do Rice tables for weak acids and weak bases, the reaction is always going to be a Bronsted-Lowry reaction of that substance with water. So this is where we're going to put H2CO3 reacting with water. What are my products of that reaction? HCO3 minus and H3O plus. For our purposes, like this equation and what we wrote in letter A are pretty much interchangeable. Okay? All right. What do I do next? Cross out water. Why can I cross out water? Because it's a liquid. All right. Now I'm going to set up my initial concentrations. What do I put for H2CO3? 0.1. And what about my two products? 0 and 0. All right, so what are my changes? x plus x plus x, because we have none of the products, we have to proceed towards the right in order for this reaction to occur. So we're going to have 0.1 minus x, and x, and x. Let's write out the equilibrium expression for this reaction. So it's going to be Ka1, and I know I'm right in your way, guys, equals HCO3 minus times H3O plus all over H2CO3. Right? Now, before we plug in, can we omit this minus x? We have to check. How do we figure out if we can omit that? The initial concentration over the Ka value. So we're going to do 0.1 over 4.3 times 10 to the negative 7. And if that's greater than 400, then that minus x is negligible. And it's significantly greater than 400. It's like 233,000. So that minus x is negligible. Another way to think about it is that the x value itself is so significantly smaller than the initial concentration that if you think in terms of sig figs, when you do 0.1 minus that really, really, really tiny x value that we're going to solve for, it's not going to be any different than 0.1, 0, 0, because of rounding and sig figs. Okay, it's so significantly small compared to that initial concentration. Just makes our math a lot easier, because then we're going to do 4.3 times 10 to the negative 7 equals x squared over 0.1. And then we'll solve for x. Okay, so go ahead and do that while I pause while you calculate. All right, so what do you get? Bless you. What do you get as your x? (2.07 times 10 to the negative 4), right? Now, what did this problem ask me to calculate? H plus concentration, not pH. If we wanted pH, we would then do negative log of that. But we wanted H plus concentration. I have not fully answered the problem. What am I missing? Units. What are my units? Molarity. And I also have to indicate that this equals the H plus concentration. Okay? Cool? Now let's handle the second dissociation. So for letter C, which for me is on the next page, now we're going to be looking at the second dissociation equation. All right. So let's start off. Oh, I went backwards instead of forwards. Let's start off by doing the rice table. What are going to be my reactants for the second dissociation? Reacting with water, forming CO3 2 minus and H3O plus. All right, I can still cross off water. What's my initial concentration of HCO3 minus? What is it? 2.07 times 10 to the negative 4, because that's what I had left over for these. This is what my x was after the first dissociation. So I have already some HCO3 minus and H3O plus from the first dissociation, which are my initial concentrations here. See how that works? What's my initial concentration of CO3 2 minus? 0. That's still 0. So what will my changes be? This one's still going to have to go down. These are going to have to go up. Why am I still proceeding towards the right? Because we have none of the CO3 2 minus. If we had sum of all of it, then we'd have to calculate Q and compare that to K and figure all that out. But for this, remember, when you have a 0 in there, that's the direction the reaction will proceed. Okay? Alrighty. So this is going to be 2.07 times 10 to the negative 4 minus x. This will be x, and this will be 2.07 times 10 to the negative 4 plus x. So let's write out the equilibrium expression. Instead of Ka1, I'm going to write Ka2 to signify that this is the second dissociation. And that equals the concentration of CO3 2 minus times the concentration of H3O plus all over the concentration of HCO3 minus. Now, can we omit that minus x? What do I have to compare in order to figure out if I can omit that minus x? The initial concentration of what? Of HCO3 minus. So the 2.07 times 10 to the negative 4, I need to compare that to what? Ka2, which is given in the problem right here. It's fairly small. By the way, the general rule of thumb is typically when you have a Ka value that's 10 to the negative 4 or negative 3 or greater, typically minus x will not be negligible. It'll be significant enough. When it's smaller than times 10 to the negative 4, pretty much going to be eliminating that minus x. So fairly small Ka value, like 10 to the negative 4, or sorry, 10 to the negative 5 or smaller, that minus x will be negligible. Okay. There's a couple homework problems, I think on 6b, where minus x was not negligible. And when I was making the key, I put a little frowny face. It's like, oh, I have to account for it. Okay. But most of the ones we're going to be doing, minus x will actually be negligible. Okay. All right. So is that minus x negligible? Yeah. When you compare 2.07 times 10 to the negative 4 to 5.6 times 10 to the negative 11, that's a really small, or that's a really large value. So that x is going to be really tiny. Is there anything else we can omit? If minus x is negligible, wouldn't plus x over here be negligible? Because if we're subtracting a really, really tiny number from 2.07 e negative 4, and that barely changes it, then adding it will barely change it. So this plus x becomes negligible as well. The plain x won't ever be negligible because it's always going to be significant compared to 0. Anything is significant compared to 0. Okay? So 5.6 times 10 to the negative 11 equals x times 2.07 times 10 to the negative 4 over 2.07 times 10 to the negative 4. So what is x? Yep, our Ka2, 5.6 times 10 to the negative 11. And that's the concentration of CO3 2 minus. Now, what did this problem ask me to solve? What did it ask? The final concentration. It wanted me to find the concentration of H plus after both dissociations. So what is the concentration of H plus after the second dissociation? .07 times 10 to the negative 4 molar. Is that any different from the first dissociation? Nope, and that's the take-home point. That's the takeaway point. All right, that's the big idea here. That for polyprotic acids, the amount of H plus or H3O plus, whichever one you're thinking about, the pH is really only impacted by that first dissociation. The subsequent ones, the amount more that's dissociating is insignificant compared to that first dissociation. I want to still go through the motions of calculating X because in your homework, after today, you should be able to do all of 6b. In that homework, there was a problem for a triprotic acid, and you had to calculate the concentration of every single substance. So I still wanted you to show you how to, get to the other things. Okay? Cool? Questions? All right, that's it for polyprotics. We're not going to do a ton of it, but that was it. Okay, now we're going to talk about salts. So page 7. All right, before we actually go through this problem, what is a salt? How would you classify a salt? What? It's an ionic compound that is not an acid or a base, right? So it's any ionic compound that's not an acid or a base. So it's not going to begin with H+, it's not going to end in OH-. All right? So it's really just any ionic compound. Typically, the salts we'll be dealing with are those that are completely soluble ionic compounds, so those strong electrolytes. Okay? All right. What do you get, or what type of reaction is it called when you add an acid to a base? A neutralization reaction, right? Neutralization reactions are an acid plus base. What are the products of neutralization reactions? Salt and water. So we're going to be kind of working backwards to figure out what the parents were of different salts. So we're going to be looking at salts, figuring out the ions that are in them, and then work backwards to figure out what acid formed, the one ion and what base formed the other ion. Okay? If you've watched the video that I asked you to watch by today, this will make more sense to you. If you haven't watched it yet, you might be a little bit lost, but then you'll have the video to refresh. Okay? So, let's look at this first one. KCN. Let's just first dissociate it. Let's figure out what the ions are. Is KCN soluble? Yeah. Typically, if there's an alkali metal, which we have one here, they're going to be soluble ionic compounds. All right, so let's just go ahead and dissociate KCN. So since it's soluble, it's a strong electrolyte, it's going to completely dissociate. What does KCN completely dissociate into? K plus and Cn minus. Exactly. That's potassium cyanide. All right. Like I said, salts come from acid-base neutralization reactions. So one of these ions is the daughter of a base. It comes from the base. And one of the ions comes from the acid. Shush. Bases typically have what in common? They typically have hydroxide. There's a couple like randos, like ammonia and a couple of those other organic bases, but a lot of our bases have OH minus. All right, so OH minus is what type of ion? It's an anion. It's a negative ion. Hydroxide is an anion. So the base, like what has to be paired with an anion? A cation. A cation. So if hydroxide is my anion, and that's common in a lot of bases, bases also contain cations, right? So my cation comes from a base. And that's how it's going to be for most of these salts, if not all. Actually, it's going to be all the salts. All the salts we're going to be doing, the cation comes from the base. All right? More specifically, what base does that come from? KOH. More specifically, that was formed from KOH. Okay? What type of base is KOH? That is a strong base. All right, now let's do the other side. If cations are typically, they come from bases, what types of ions come from acids? Anions, and that makes sense because acids typically have H+, so they have to have an anion to go along with it to balance it out. So therefore, my Cn- comes from an acid. And in this particular case, it would be HCN, which is a weak acid. There's that carbon, it's weak. Okay? Now, there's several different ways. This is like one of the more challenging concepts of this unit, and some of you are trying to sleep during it.
Come on, Brandon.
So, there are several different ways to think about what type of salt this is. Not all salts are neutral salts. Some of them have acidic or basic properties. In your guided notes on page, I think it was 18, if you have your guided notes with you, I'm fairly certain it's page 18. It has a little like chart, or like it tells you the different combinations of types of acids and bases. Yep, is that page 18? No, that one right there at the bottom of the page. It's not a chart, it's just the four. Yeah. Oh, okay. So that page tells you the different combinations of the different types of acids and bases and what types of salts they make. So for example, a strong acid and strong base will be a neutral salt. Strong acid and weak base will be an acidic salt. Weak acid and strong base will be a basic salt. And if both the acid and base are weak, you have to actually look at their K values. We're not really going to be dealing with that. The textbook goes through problems of that. I'm not going to hold you responsible for it, though, because that's beyond what College Board wants you to know. All right? So, you can just memorize that. Think about it this way, like whichever one's strong, that's the one that kind of wins out with it. So for example, for this one, we have a strong base and a weak acid that made this salt. So this salt is a basic salt. So therefore, its pH would be what? Greater than 7. And that's my answer, because that's what I asked in this problem. Now, what happens in water? The reason this is a basic salt is because the ion that came from the weak substance will hydrolyze with water. We'll do a Bronsted-Lowry reaction with water. Only the ion that comes from the weak acid or weak base. The one that comes from the strong acid or strong base is like a spectator ion. Like our alkali metals, we never care about them. They're there, but they don't influence our pH. So only the Cn- is going to hydrolyze with water, which is a Bronsted-Lowry reaction. Okay, so what ends up happening is that Cn-, like when you add KCN to water, it does completely dissociate. And then there's this like secondary reaction that occurs between the Cn- and the H2O. And so what would the products of that reaction be? HCN and OH-. Do you notice how we produce hydroxide ion, which indicates that this is a base? It would make H3O+. Exactly. Okay? I'm glad I finally taught you something in this class. Okay. Cool? Do you want to do another problem? Yeah. I think we should do another problem. And I also think we should stop talking while I'm trying to teach you. So, we're going to write the dissociation equation that describes what happens when CH3NH3Cl is added to water. So this is just like the first part we did with problem 15. Okay? So CH3NH3 Cl. We're just going to put that in water and dissociate. That's a salt, so it's just going to split up into its ions. So what are the ions that forms in water? How did you know those were the two ions? You guessed? Well, you guessed correctly. Ways that you can think about it. What? Yeah. Ways you can think about it are typically, like, if you see Cl, that's gonna be like the standalone, and the rest of it will be the other ion. You also could have looked ahead at problem 17 and seen that was an ion. But it's okay if you didn't. I like that you're focusing on the one problem at a time. Okay? All right. But we're done with 16. Well, now, what part of 16... No, okay, let's go through it. What part of 16 is going to hydrolyze, if any? Well, the chlorine comes from what? This comes from HCl, which is a strong acid, so therefore we're not going to hydrolyze that with water. So therefore this substance here has to come from a weak base. Because, first of all, the only ones that are going to be coming from strong bases are going to be your alkali metals and then strontium and barium, right? And that isn't any of those. They can both be strong, but they would have both been strong if this was like sodium or potassium or lithium, you know, one of those alkali metals, or strontium, barium, okay? So this has to come from a weak substance, so this is going to hydrolyze. Which is what we're going to do in number 17. So 16 and 17 go hand in hand. They're like, really it should be 16A and 16B. Okay? So, we're going to hydrolyze CH3NH3+, react it with water, do that Bronsted-Lowry reaction. Which one's my acid here? The CH3NH3+. That is my acid. Now, shush. How do we know it's my acid?
Because it produces it's a cation.
Oh, okay. Okay, all of those. Okay, yeah. Yes. One way we know that this substance right here is an acid is because it literally asked me for the acidic character of that. So that means that this has to be acting as an acid. Also, since Cl- came from my strong acid, that means this comes from my weak base. Therefore, this is a weak acid. Because it's always opposites, conjugates. Conjugate acid, conjugate base. CH3NH3+. The weak base formed it.
Also, when you do it, wouldn't it be like CH3NH3OH plus H plus?
No, so when we write the Bronsted-Lowry reaction, remember we're transferring a proton. We're transferring a hydrogen ion. So from the acid to the base. If this is my acid, this is my base, what are my products? CH3NH2 and H3O plus. And since we formed H3O plus, that means that this was acidic, which means my salt was acidic. So what would my equilibrium expression be? Right? Like that. Cool? Now, honestly, for these types of problems, you're going to be given more information. You're going to be given some equilibrium constants, like in the next problem. Okay? It's not going to be so open-ended where you're like, oh my god, I have to know from the structure. You're going to be given some other clues. All right? That will help you along the way. The main job, the most challenging part, is recognizing that you have a salt and not a weak acid or weak base to begin with. All right, that's going to be your challenge right there. Okay? Ready to do the next problem? Number 18? All right. For right now, I'm telling you that we have a salt. Okay? We have sodium acetate. That is a salt. What type of salt do you think that is? What are the ions in sodium acetate? Na plus and C2H3O2 minus. All right. Will either of those ions hydrolyze with water? Na will not, because Na really comes from NaOH. That was like the base that formed, that provided the Na for this salt, the Na plus for this salt. The base in the acid-base reaction was NaOH, which is a strong base, so we can ignore the sodium. You can ignore all alkali metals, and you can ignore all halogens, really, because they're always going to be coming from strong acids and strong bases. So therefore, the C2H3O2 minus, that comes from what acid? Acetic acid, which is a weak acid. Okay, which is a weak acid. So we have a strong base, weak acid. So what type of salt is this? This is a basic salt. Therefore, let's predict our pH. Should be over this. It should be greater than 7. So when we do our calculation, hopefully we get something larger than 7. Okay. Yes, for basic salt. If it was an acidic salt, I'd put AS. All right. Excuse me. So my rice table, my R is going to be the Bronsted-Lowry reaction of the ion in my salt that comes from the weak substance. So it's going to be C2H3O2 minus reacting with water. What are my products? Acetic acid, HC2H3O2, and OH minus. Now notice that C2H3O2 minus is a base. Notice how the Bronsted-Lowry reaction of my ion from my salt reforms the weak acid that formed it to begin with. Same thing back here. I'm going to go back a page. I'm going to go back one more because this one's a little easier to understand. Same thing back here. Cn minus, we know it came from HCN. So when it reacts with water, we get back some HCN because these are weak substances. Okay? So here, we get back HC2H3O2. We get back acetic acid. So cross off water. Let's fill in what we know. What's my initial acetate ion concentration? 0.700. Why? But wait, that concentration is for sodium acetate. How come I can say it's the same for acetate ion?
Because for every 1 molar sodium, there is 1 molar.
Yeah, first of all, it's a 1-to-1 ratio between the ions. And this is what type of electrolyte? A strong electrolyte, which means it's completely dissociating. We learned that back in Unit 2, that when you have an ionic compound, when you dissolve it in water, the concentration of the ions are related to the overall concentration of that entire compound. You just have to multiply by the coefficient in front of the ions. This is all 1-to-1, so the concentrations are all the same. Okay? What's my initial concentration of my two products here? 0 and 0. So what are my changes? Minus x plus x and plus x. All right. Let's write the equilibrium expression. What subscript am I going to give my K value? Or my equilibrium constant? It's going to be K what? Notice how we have hydroxide as a product. That means this is a base. So we're going to write a Kb expression. So in order to solve for the pH, I need the Kb of the acetate ion. So I look at the problem and I realize, oh no, I must have done something wrong. I have a Ka of acetic acid. What is the relationship between Ka and Kb? No, you cannot just cross off A and turn it into a B. If you look on your formula sheet, which I know you don't have out in front of you, there is a formula on there that says this. Ka times Kb equals Kw. We haven't used this formula yet, but this works for all conjugates. The Ka of a weak acid times the Kb of its conjugate base will always equal Kw. And Kw is 1.0 times 10 to the negative 14th, which is on your formula sheet. Kw is a constant at 25 degrees Celsius. We won't be dealing with non-25 degrees Celsius. All right, so I gave you the Ka of acetic acid, which is what you would find in like a reference table. You need to calculate Kb of the acetate ion. So we're going to take 1.0 times 10 to the negative 14 and divide it by 1.8 times 10 to the negative 5. And that will give me my Kb, which is what? 5.6 times 10 to the negative 10. And we're going to use that Kb to compare it to the initial concentration to figure out if that minus X is negligible. And is it? Yes. So 5.6 times 10 to the negative 10 equals X squared over 0.7 molar. So now you can solve for X. So when you're given a problem like this, when you're given a salt, an easy way to know that you have a salt is you'll always be given, like for example, here, we're given a basic salt. Whenever you're given a basic salt, you'll always be given the Ka for the weak acid that helps form that salt. And if you're given an acidic salt, you'll be given the Kb for the weak base that helps form that salt. So you'll always be given the K value for the opposite thing. So that's another indication when you're looking at this. If this were a problem, notice I didn't give you a K value for NaC2H3O2. I gave it for something that was just a conjugate of one of the ions. So that should be a hint right there that, ooh, this is a salt. I'm going to kind of do things backwards. Okay. All right. Have you solved for X while I talked? What did you get as your X? 1.98 times 10 to the negative 5. And what concentration does that equal that will help me get to pH? The hydroxide concentration. So if I do negative log of that, that'll give me POH, and then I can do 14 minus that to get to pH. So what is my pH? Because we want 3 sig figs, we need 3 decimal places. Always look at your initial concentration for sig figs. Never look at your K value, because K values are constant. They're like standard values. Always base your sig figs off of your initial concentrations. Did this pH work for what we predicted? Yeah, so we most likely did the problem correctly. The number one thing people do here is they take acetic acid and put it in water. But this isn't a weak acid. This is a salt, so we're working backwards. Okay. I want to walk you through a few things with the next problem. We're not going to do all of number 19. There's 19A through D. We're not going to do all of 19. We're going to do one of them, but I'm going to give you K values for the other 3. Okay? In your textbook, at the back of the textbook, there is appendices of, there's like an appendix that's a bunch of different charts, like Ka values of some common monoprotic acids and Kb values of some common weak bases. When you're doing a problem like this and you aren't given a Ka value in the problem, like for example, number 19a, you're not going to see KClO or ClO minus in any chart. Instead, you'll see HClO. Actually, it's written as HOCl because of the way that the hydrogen's attached to the oxygen, but it's the same thing. You're going to see this, and you're going to be told that its Ka value is 3.5 times 10 to the negative 8. All right? But you're not going to see actual ClO minus. So when you're looking it up, you're always looking for the weak acid or weak base that made it. Okay? For example, here, you're not going to find NH4+. Actually, you will for this one because that's a common one. But NH3, Kb equals 1.8 times 10 to the negative 5. Again, if you're given a Kb value, that means what type of salt is it? Acidic. If you're given a Ka value, that means the salt is basic. It's always the opposite thing. Have you guys written down those two K values? Because I have to switch to the next page. So go ahead and write down those two K values so you don't have to look them up later. You're going to have to look things up for your homework. So you get practice looking things up in the chart. Well, for the test, it's going to be more like number 18, where it'll be written right there in the problem. Just for your homework, though, you get to practice looking things up in the chart. Okay. Have you guys written both of those? Okay. Let me give you D. Well, I mean, I did just look them up during 7th block. And if you notice, the Kb of ammonia and the Ka of acetic acid are the exact same values. 1.8 times 10 to the negative 5. And I've been doing this for like almost 20 years. All right. We're going to do number 7 together. This is going to be the last problem for today. It's going to be the last problem for today. Number 7. What are the ions in number 7? Oh, what am I saying? Am I saying number 7? What am I saying? Letter C. C7. Letter C. Sorry about that. You can keep it. Letter C. Not number 7. Letter C. We have K plus and Cl minus. K plus comes from what base? Which is strong base. Shh. And Cl minus comes from what acid? Which is a... So what type of salt is this? It's a neutral salt because strong, neither one wins out. Therefore, what is the pH of this solution? 7. Cool? Now, the other 3 are going to be more like number 18, so you get to practice that. And the second video is all of this stuff as well. So you get, maybe he'll explain in a way that makes more sense to you if this is a little confusing. All right? Just reiteration.